Hello. I found AROW kind of difficult to really get my head around because I guess it's not a simple idea. It's trying to balance lots of things. It's kind of just throw a bunch of stuff together, tweak some parameters, and it should work well. Um, so anyways, I've thought about it a bunch, and in this screencast I'm going to talk about some of my thoughts about what AROW is really doing and how to create a good algorithm like this. And I haven't gotten it all figured out, but hopefully you'll find some insights that will help you as well. So first of all, I want to go over some what I'm calling problems here. I don't think they're actually problems, but they seem to be, I don't know, inconsistencies, or they look kind of fishy. So first of all, why should the confidence increase more when you have a larger x? So let's say here, roughly we've got this margin, right? And so let's consider maybe we've got a point here or a point here. Here, this point is just as close to the edge as this point, just as close to being over the margin as this point. However, for this point, we're going to make the confidence much smaller. So does that make sense? I don't know. I think in very high dimensional space, when you have the scale in each dimension about the same, I think it might actually make sense. But it's just hard to say, and it seems kind of fishy. So I'm considering this term here. When we have larger x's, we've got stronger, in the minimization, we've got stronger pressure to make sigma smaller in that direction. And another thing is we only minimize this when this margin, when the margin is greater than, or when the loss is greater than 0. So if we're on this side of the margin, the loss is greater than 0, and so we need to do an update. So this seems kind of funny because, okay, so if we had a point here, we would do an update and we would change the confidence, right? If we had a point here, since x is getting bigger, we would reduce the confidence, we'd increase the confidence even more for a point here than for a point here. However, if we move just to the other side here, all of a sudden, since the loss now is 0, since we're on the other side of that, here the loss is tiny, but still positive. Here the loss is 0, so we're not doing an update, and so we don't change the confidence at all. So the amount that we increase the confidence by, here it's nothing. It increases, then all of a sudden, no change in the confidence once we cross the other side. So it just seems kind of fishy. So there might be a better way. I'm guessing that this wouldn't make too big of a difference in the performance. Right. So I have more questions. So when should the confidence increase? Should it increase for ones that are definitely correct? So if we consider this point here, which is definitely correct, should we say, okay, since that was correct, should we increase our confidence? I would say no, since the direction of our vector should really depend on these marginal points, right? So whatever we have here shouldn't affect the direction of our vector because it's definitely classified right no matter what. So should it depend on the ones that are definitely incorrect? Well, I think, again, no. I mean, this one is basically a mistake. And so when we see this one, I don't know that we should actually make our confidence. I don't know that we should actually increase our confidence. Yeah, if it's one that's clearly incorrect. It's more when we It's these ones that are defining the boundary between what is basically blue and what is basically purple. It's for those ones that I think we would actually want to increase the confidence. So my answer would be the marginal ones, since they're what define the boundary. So I kind of had an example of this in my mind. So I'll create a boundary like this. So that's the boundary, and I'm going to make a separable case. We've got a bunch of points here, and just a few points here. And then in the other color, we've got a bunch of points here, and just a few points here. So this is the boundary we want, right? And so ultimately, we're going to want our vector to be, in that direction, pointing towards the blues, right? And so it really shouldn't be affected by this mass of points. It should only be affected by the points on the boundary, and it also shouldn't be affected by how many points there are, right? So, yeah. So only the really marginal points should matter. And the points that are misclassified shouldn't really matter. And the points that are totally correctly classified should not matter. So when should the confidence increase most? Well, presumably in these marginal cases. Yeah. And so in this case, we might quickly sample a bunch of points up here and a bunch of points here, because there's lots of points above and below. And so we might quickly figure out that, okay, we want an upwards component in our vector, right? I want to do that in this color. We want an upwards component in our vector. We might not have sampled many of these yet. And so we would want to have our confidence be something like this. So we're pretty sure of the upwards component. We aren't that sure of this component yet, because we haven't sampled many points that are much to the left or the right. And so then later, as we have lots of data, eventually we start sampling some of these points, and then our vector would tend to rotate more that way, and this confidence would decrease a little bit. So that's my thought. So when should the confidence increase the most? Well, you should increase, the more marginal cases you have, the more the confidence should increase in the direction of those marginal cases. Now, as we get more and more samples in a given direction, how should the confidence in that direction decrease over time? And my thought is it should decrease something like 1 over n. This way, so this is a similar intuition to what you do for stochastic gradient descent. 1 over n decreases over time, so the stochasticness will decrease over time. So your randomness decreases from there being a bunch of different points. However, since the integral of 1 over x dx is equal to infinity, if we kind of make an early error, right, because we get a bunch of points in one direction that are wrong, we can correct this over time, because these basically a bunch of updates like this add up to infinity. No matter how big n is now, we can correct any error. And this seems to be exactly what this algorithm is doing. So for each update of u, we can see, I'm assuming sigma is getting smaller over time, so eventually we can just ignore that. R will be bigger than that. And then, well, this could be bigger or smaller. I'm going to ignore that part. What I want to focus on is this part. And so as sigma gets smaller, these updates get smaller. Now let's look how sigma gets smaller. Well, sigma inverse, we keep adding this. So if we keep adding this in the same direction, that means that sigma in that direction will be proportional. Sigma will be proportional to 1 over the number of updates in that direction. Because assuming we do roughly the same update over and over, right? And so therefore our updates of mu in that direction will also be proportional to 1 over n. And so this seems to be exactly what this algorithm is doing to make sure that it always converges. Now I had this other idea. Should we encourage mu to decrease over time so that we are actually maximizing the margin? And I think the answer is maybe, but this probably isn't worth it. And what you'd have to do, since we have more updates in certain directions than in other directions, we would actually want to decrease more in the directions of higher confidence. So that would be something like multiplying by a root of sigma. So in directions of high confidence, we decrease more than in directions of lower confidence. So this might cause some really marginal improvement, but I don't think this is worth it. Probably not worth it. Although possibly, yeah, I don't know. I think it's probably not worth it, based on the examples I've thought of where this might cause some marginal improvement. Now, how much should we change u, and when? So it seems to me like changing mu proportional to x is a good idea when there are a bunch of 0, 1 features, right? So in natural language processing, we have a bunch of 0, 1 features, and hence the component hence we'd like to make updates in each feature proportional to the number of instances of that feature. Now the interesting thing is if we do this, there's some features that are really common. So if we have some vector, right? Or say we've got some vector here for an update. Well, the component of our vector in the downward direction, because the downward and upward are very common feature directions, will not change much, whereas the component in that direction will change more, right? So it's kind of, this algorithm is really good that way. So you initially make a bunch of updates in this direction, then over time your updates tend to be more in the directions that you haven't updated much yet. So this is really good. This is also good. I want to draw another example. Sometimes, so let's take a simple example. I'm going to take a simple example, something like that, and like that. I'll erase a few of those. And now something that you may know about is with the perceptron, things really change as we change the scale. So that's what I'm going to try doing here. So here things would work great with the regular perceptron, but let's change the scale to something a bit more like that. And I'll extend the axis. So I've squished it horizontally. So now the separating line should be something like that, right? Which means that we want a vector in that direction. However, initially what we're going to do is we've got a bunch of blue ones up here, a bunch of pink ones up here. And so for the most part, we're going to have updates up and updates down. So we're going to kind of go, yeah, we're going to have updates like that. Occasionally we'll have updates in the opposite direction. But overall we'll have more updates like that. But then over time our confidence in the up-down direction will increase. So our confidence will start to look something like that. We're very confident in the up-down direction, not so confident that way, which means we're going to stop updating in the up-down direction so much. But we'll keep updating in the left-right direction. And so over time, our updates, our updates will tend to be more left and right, which will mean that over time, this will tend to shift and become more in the direction it should be in, which is really cool because, again, because our confidence is directional, it helps to deal with this problem of scale. Initially it will increase quicker and converge quicker in the up-down direction, but over time we'll get the horizontal components as well. So that's pretty cool. Pretty cool. Right. And so I was thinking, in terms of when, if something's obviously misclassified, then maybe we shouldn't update mu, right? However, maybe something seems to be classified, but if we look in really high dimensions, there's some features that we rarely use. Whereas if we use those features, we could classify this correctly, right? So then maybe, although this looks misclassified based on the common features that we have used to update everything so far, maybe actually there are some new features we can use to classify this correctly. And so that's why I think, again, changing mu proportional to x is a good idea. Because in these new directions, where the confidence is still very low, we're going to, if we've got a 0, 1 variable, so we've got, I guess, a feature of 1 in that direction, well, then we're going to be doing a full update in that direction, that kind of new direction, which will help us classify this point correctly in high dimensional space. So I think in general, if we know something's obviously misclassified, there's not much point in updating mu, but we might as well always update mu, because when we're working in very high dimension, maybe it isn't actually a mislabeled point. Maybe we just need to use some uncommon features to classify it correctly. So I think being updates proportional to x makes sense. I'm not sure. Yeah, I'm not so sure that the update should be proportional to the loss here, because for this point the loss might be very large. And so then we have an update proportional to the loss and proportional to the size of x. And so it's, yeah, we could have a very huge update, which, we've got our vector in this direction, and then we have a big update in that direction, so then it's too small, and then we need a bunch of updates in this direction to restore the margin, that's as large as we want, right? So I'm not sure about this part, but anyways. So I guess I'm not sure about this part when maybe cap this at 1. That would be one of my ideas. So that, yes, as the margin gets bigger, we're going to make bigger updates, but when it gets really big, where it may be due to a mislabeled training point, maybe we don't want to make huge updates there. So that's why I'm thinking maybe cap this at 1. Just an idea. Right, and so that was this second point here. When the margin becomes very large, maybe due to a misclassified training point, so I don't think we should change it too much. Overall, the idea I think the idea of this is the idea I've presented that I think underlies why this works. I think the idea is kind of like stochastic gradient descent, but since we're working in very high dimensions, we want to make this decrease proportional to 1 over n. We want to make this directional. So we want to do kind of each dimension or each direction. We want each direction have its own factor of 1 over n. And that's what this matrix does, which is really cool. All right, those are some of my thoughts. I hope you find this interesting and insightful and useful. And if you have your own insights that build upon this, I would love to hear them. Thanks for watching.